for our first talk of today, we are very fortunate to have Professor Qiang. So he will be joining us from Zoom later. So for now, we already have a recorded video of his talk. So my colleague will start the video. Meanwhile, let me introduce Professor Qiang. He's a Chief AI Officer at WeBank and Chair Professor and former Head of Department of Computer Science and Engineering at Hong Kong University of Science and Technology. His research interests include transfer learning, machine learning, planning, and data mining. And he was also a founding head of the Hong Kong division of Huawei's Noah's Ark Lab. So his topic today is trustworthy federated learning.
Hello everybody, I'm very happy to speak at the summer school. Today I'm going to talk about trustworthy federated learning. Let's first start by looking at some examples. In finance, it's often the case that when new users come to applying for accounts or for bank loans, they need to go through a process of risk credit control, risk assessment, as well as anti-fraud operation to verify whether the application is legitimate. Such applications usually need to be handled by data and models from multiple parties. And here, multiple parties could mean a bank, a finance center, a data center, or other institutions that record data about the user. When such a collaborative assessment happens, it is important that each institution or party does not reveal its data to others. And yet, it is also important that all the data and models located in these participating parties are useful. That is, they can contribute to a global model. So in this situation or example, we face a two-pronged objective. On one hand, we need to have a global model using all the data and models to make a decision. On the other hand, our global model cannot reveal the privacy and secure data from any participant. So how do we solve this problem? Another situation is financial credit rating, which is very similar to anti-fraud. In this situation, we not only need data from the finance institutions such as banks and loan institutions, but also other digital enterprises such as e-commerce or news medium or video mediums that may tell us something about the user behavior and can reveal the user's preferences. And here on the picture, I show institutions such as Facebook, Twitter, as well as others. All these data can be very useful, and we therefore need to solve similar problem as the previous example, which is, on one hand, we need to make a decision on this user. On the other hand, we need more behavior data, which is what we call the X attributes from other institutions which may not be finance. So in machine learning terms, we know why we need more X. And with X and Y together, we have a more sophisticated model of the user. Similar things can happen with the hospitals and medical practices, where we have many examples of multi-center, multi-data center joint work. For example, a hospital may do a medical check on a user and may need data from multiple medical institutions. And we have the same problem. On one hand, we need to control the data privacy. On the other hand, we need an accurate model. The same thing happens when we have a drug design company that will need data from multiple medical data centers. But to do such a thing, that is to use data from multiple centers, is getting increasingly difficult. Not only because all the society is aware of the importance of protecting privacy, but also there are many laws that are in place to control, to regulate such activities. We have seen on the media reports on such as giants like Facebook and Google being fined by European lawmakers on violating such security laws. Okay, and in Europe, for example, the GDPR, which is the famous law for protecting individuals' privacy, is being very strictly executed. On Netflix, there is a documentary on Cambridge Analytica, which is about how such a collection of data can be easily misused for biasing voters' choices.
Okay.
In China, the data security laws are also more complete and more strict. And there are 3 laws that are introduced in 2021 concerning personal data privacy, data security, and cyber security. In this background, we need a solution that is jointly in place from technology practitioners and law practitioners. We need both. And from technology perspective, this is the topic of my talk today, which is what can engineers like us provide to safeguard our data and yet allow the flow of information, data, and model to drive a digital society. And federated learning come to the rescue. And what we can think of in federated learning is an analogy. On the lower right, I have a picture where we want to raise a model. And this model has to get knowledge or nutrition from multiple parties. And our restriction is that none of the data that feeds the model can go outside the location of the party. And so in order to grow the model, a choice we can make is to let the model visit each site instead of let the data travel out. And in the process, we should protect the model parameters so that no party can illegally peeking into other parties' data and can learn something about the model that are not permitted. So in this background, we have several choices. We can make the model very, very advanced and very secure, and yet it may be very inefficient. And so our task is how to very smartly design this system so that it can be useful and it can be very secure. And there are 2 related paradigms that are designed to accomplish this goal. One is led by Google, which is shown on the left. And in this picture, we have what's called a horizontal federated learning picture, which allows multiple devices to collaborate together to build a joint machine learning model. On the upper right, we have a model known as vertical federated learning that is led by WeBank and colleagues in China, which is a to-B version of the federated learning to business. That is, we have two or more businesses that can collaborate by complementing each other's feature space. Features are behavior. And so these two pictures, one gives the to C to consumer solution, and the other gives to business solution. But there are many other key components we need in building a federated learning system. So federated learning is no longer a single discipline, rather it's a multiple discipline coming together. In computer science alone, it touches on privacy and security and encryption and decryption. It touches on AI, which is about model design and model training. It touches on game theory, economics, in terms of designing a sound incentive mechanism to grow the ecosystem of data and models. It touches on communication networks, on how to optimize the efficiency and effectiveness of the network. And finally, distributed machine learning. So in order to answer this, there are several textbooks published, including our book, which was published about 2 years ago. So to visit again the fundamental concepts of federated learning, horizontal federated learning can be seen as where we have data partitioned by samples. So each data center holds a number of samples. Another data center holds other collections of samples. But these samples share a lot of features. For example, each one is operating some security camera. And although they are about different regions in the city and therefore about different samples, their features are mostly the same. That is, the pixels and properties of the pixels, such as color, depth, and so on. So this situation is more feasible for edge computing. For example, we have multiple sensors across a railway. And we have these sensors collecting data to build an overall picture, and they need to collaborate with each other. And we can have multiple unmanned vehicles, autonomous vehicles operating in a city, and each one corresponds to a small-scale data center. And they need to communicate in order to build a more powerful overall model for autonomous driving. In contrast, vertical federated learning is usually about institutions and businesses collaborating together. For example, we may have party A being a bank and party B being an e-commerce company, or party A being a taxation company and party B may be a auditing company. Okay, so these are businesses working together to build a joint model. And what they share may be samples, and what they complement may be features. And therefore, the data are partitioned vertically. It's like cutting a table apart vertically. Both are very useful, and in particular, horizontal federated learning has seen a dramatic rise in the amount of research. And vertical federated learning there's a resurgence. For example, in November this year, a group of researchers came together to redefine vertical federated learning in terms of what it is, its security, and its many applications. And it can be downloaded from this archive link. So the picture shows exactly how vertical federated learning works, where we have multiple parties. We have 3 parties, and they all work with a coordinator which is located on top, yet they don't have direct communication with each other to ensure security. And in doing this, we must observe very strict security in order to protect the both the data and the parameters of the model. And on the right-hand side, we can see several levels of securities from basic, standard, all the way to very, very strict, advanced, according to how their communication is designed and how their encryption mechanism is enforced. And there is a trade-off between effectiveness, efficiency, and security. And this trade-off in particular is our subject of discussion in trustworthy federated learning. In particular, in this area, there are works emerging on different types of attacks, such as data inversion attack and backdoor attacks. And this survey covers them both. A real example is a forest model. A famous forest model is the XGBoost boosting model on simple decision trees. And in a horizontal federated learning version, this model has been realized in a open source software called Fate, which is part of the Linux Foundation software. Its vertical counterpart is also available. And we have on the left a horizontal and on the right a vertical version of the tree model. And in both models, partition is on the model is done by partitioning the forest into subforest. And so each submodel is a subforest which is part of the overall global boosting model. I mentioned earlier that federated learning has grown to be a multidisciplinary research. And people from economics, from business, can enjoy research in this area as well. For example, how to design the best incentive mechanism in order to distribute the income fairly among participants. An example is when we have multiple data owners, and when they join a federated learning ecosystem, they collectively build a global model. When the global model is getting more accurate and therefore receives some income, how do we distribute this as incentive back to the data owners? And how to do this fairly so that people with more valuable data can contribute continuously, are more encouraged to contribute continuously. So this is an ongoing discussion topic. And yet another issue is very similar to operating system. When we build a federated learning system, we are building an operating system on data owners and model owners. Okay, so we can say federated learning is a AI equivalent of the early Windows and Unix operating system for computers. To illustrate this, before we have standard federated learning, people cannot communicate well with each other, and they build one-off modules and one-off platforms that can only be used by a very, very few experts. For example, very similar to when we build a house, we used to dig a hole in a mountain on the left. But in the modern society, when we build a smart city, we usually do not build a one-off solution. Instead, we use standard parts that are secure. And we have the entire building code on how to put the parts together in a secure way. And all these are thanks to a collection of modern standards. Similarly, in federated learning, we should have standards for building federated learning system using the standard parts, such as encryption, such as differential privacy, such as secret sharing, such as distributed AI, vertical and horizontal federated learning paradigms. Now, there are also a lot of community work in this area. A survey was recently was published in 2019, and subsequent surveys are updated, titled "Advances and Open Problems in Federated Learning," and starting researchers are encouraged to visit this survey. So we want to look at some examples. Like I said in the very beginning, a very first application area for federated learning is in banking. And here we have financial institutions, payment companies, money lenders, e-commerce companies, and other online digital entities. On the other hand, we have many other seemingly irrelevant but data-rich companies, such as internet companies, e-commerce companies, and other data services, such as telecommunications operators. Now, federated learning allows us to combine all these together in a very secure way. And for example, in our application, we were able to increase the amount of the number of data sources, and therefore the amount of data participated in the credit model building. And as the blue line shows in the lower right graph, we can see as the data increases, the capability also increases, exceeding the red line, which is what's useful in what can be used in finance. And the automated model building clearly surpasses this rate. In smart city applications, we have camera surveillance, and this particular example, we use federated learning to join different security cameras together across construction sites in the city. And so the ability for these security cameras to detect unsafe construction worker behavior, such as fire and smoking and other unsafe behaviors, increased by a lot. Today, on our mobile phone, various applications are powered by recommendation systems that are personalized. For example, video, like TikTok, like news, and games, and others. Okay, and these data are increasingly from different parties, and they need to be combined in a federated learning way. And in this topic, there is a new area in recommender systems known as federated recommendation systems, where the data is easily decomposed by matrix decomposition, which are located scattered in many parties. And when you combine them together, you can rely on horizontal or vertical federated learning systems. In a very encouraging news from the DeepMind company and from many drug design companies, AI is becoming indispensable in new drug design. And drug discovery from multiple data sources are therefore becoming a reality. And immediately the people face a data shortage problem and need to ask, how do we combine data from multiple medical centers about users, about drug experiments, and yet we protect the security and privacy of this data. For example, in different hospitals, the medical data are highly sensitive in terms of user privacy. And we have seen many articles in bioinformatics journal in Nature and in many other ADI conferences related to drug design and biological bioinformatics. Like I mentioned, the news recommendation on mobile phone system, we actually applied this on Caixin, which is a famous Chinese official news dissemination company. And they used our engine for federated learning for combining different data sources together, and we were able to achieve very good personal news KPI, such as page view, click-through, and so on, without worrying about data leakage. In traditional AI areas such as computer vision, speech recognition, and natural language processing, federated learning is becoming also important. For example, in our application of speech recognition on multiple data sources, federated learning allows us to combine data from different clients and from different data centers. These data cannot be straightforwardly combined and integrated, and so therefore they have to be carefully managed using federated learning. And the joint model is becoming more accurate, especially on personalized speech recognition. In a recent joint work with Tencent, our researchers are able to work with the hospitals from Hubei and come up with a solution for designing, for detecting early signs of stroke. And this has been published in the Ichikai workshop paper. There are many applications such as online customer services, anti-fraud, and online teachers for human operators. When we touch on security, we have to ask the question, even though we provide some support on security insurance, can some party inadvertently get hold of the original data by just watching the parameters such as gradient and loss information? And the answer is yes. If parties work together and one party observe unprotected parameters from another model, they can reconstruct the original data of the other party. Here's one example where we have a 0, which is a character from one party, and we have on the right, we have a guessing result from another party. This party only observed the gradient and loss information from the participating institution. And if we are not careful and we do not infuse enough of the noise data, we can still reveal a significant amount of the original data. And this has been a system known as deep leak and has caused much concern in the security of federated learning community. There are also other ways to attack a federated learning system, just like we can attack an AI system. An AI system builds on training data, and when these data come from multiple parties, there are rooms where a bad party can modify some labels for the data or features for the data, and can affect the overall model as a result. So on the left-hand side, we can see a paper on how to backdoor a federated learning system, and on the right, we can see how the information can be leaked using a adversarial network, using deep learning. And worse yet, multiple parties can collude in a evil community in order to bring down the performance of the overall model. We face very similar situation when we review papers for large conferences, and there are always a few bad reviewers who collaborate with each other, who collude with each other in order to pass on their papers in a very unethical way. So the question is, can we detect a robust system to safeguard against all these attacks? The previous attacks I mentioned are called semi-honest attacks because they don't bring down the performance of the system. Instead, they steal the secrecy of the data. This one, the Byzantine attacks, are aimed at bringing down the overall performance of the system. And so it becomes a very hot topic in the research community how to design robust solutions against all these attacks. For example, we can use a graph mining, a deep graph network to detect pleas that exhibit Byzantine colluding behavior. And the behavior allow us to build some algorithm based on uncut segmentation. And the behavior has been compared with some baselines and shown the robustness improved. Back to the standard, there's a springing of new standard both internationally and nationally in China. Internationally, the IEEE standards and other international standards have already been established for federated learning. A recent development is China Telecom is leading a group of participants to build a security standard for federated learning. And Chinese Industrial Ministry is leading financial and telecommunications standards of federated learning. In open source software, I mentioned Fate as the first open source software, and that is donated to Linux Foundation. And this platform is now gaining popularity. It has more than 1,000 participants joining in, making contributions, and many more users from different parts of the society, such as industrial users, commercial users, as well as university students. One thing I haven't mentioned is building the federated learning system not just as an algorithm module, not just as one component, but as a life cycle management across the lifetime of the application. For example, when we build a data exchange, just like stock exchange, we have a model changing hands from one party selling the model to a party buying a model. So we need to trace the model and audit the model as it travels at different parties. We need to ask the question, who created the model? What data are responsible for creating the model? Which part ownership has the model gone through? And where the model is located currently. And so the situation is very similar to copyright or IP right of a book, or copyright or IP right of an art. And in order to ensure the auditing of a model using the FED IPR, we developed a system to inject watermarks into a model. So watermarks are like fingerprints that are secretly injected into a model. For example, in a deep neural net, we can use the noisy vector as as a fingerprint and we inject it into some layer of the network. And through this fingerprint, we can discover something else. We can discover who's steal, people who try to steal the model, who are not contributing but are benefiting from the model. These are called free riders. Okay, and overall, we can help building this system by allowing multiple watermarks to exist, coexist in a model. And we have very fast evaluation and assessment abilities as well. Another issue that is important and gaining speed is explainability. When we build a global model to use from multiple local models and local data sources, the model is becoming more and more like a black box. Because people keep their security and parameters of their model, the transparency of the overall model is becoming a major concern. And here we just recently published a book which is called Explainability of AI. And explainability of AI models, especially to different users, the explanations should be different. Okay, and explainability is a way to measure how transparent a global model is to different users. And even though federated learning has appeared only for a few years, more like 5 years, 4 or 5 years, it has already gained recognition, such as being added to the hype cycle of privacy in Gartner's report. So to summarize, federated learning is a way to scale up AI while protecting security and privacy by allowing a distributed AI model to be built while keeping the data or the data local. And when doing this, we have to balance and trade off security, efficiency of building the model, and effectiveness of the final model. These three issues cannot be reached cannot reach 100% at the same time. And therefore, it is important for us to ingeniously design an optimized model based on these three objectives. Thank you.
Any questions? Incidentally, today is also his birthday, so a lot of things going on the side.
So one of the things you did mention about the couple of use cases falling from banking to the pharmaceutical to the drug development, right? So one area is more from privacy and security part of it. So we need the data, but at the same time we don't want to compromise the privacy piece of it. How do we get that the data? Like I think they did mention about that the sharing the local data without revealing the complete information of it. So how do we get the data to make it more meaningful for the development of the drugs and some of the use cases which we are working on?
It's a very good question. So privacy is only one aspect of federated learning. Another most important aspect of federated learning is also how to handle the heterogeneity among the devices or among the silos that are participating. Could be heterogeneity about the data distributions, could be heterogeneity in terms of computational power, so that there could be delays in terms of people submitting results back. It could be heterogeneity in terms of the capability of deploying models to these devices. So there's a lot of work going on in that area as well, apart from privacy. So the main idea of protecting privacy in federated learning actually stems from something that's developed in 2005. At that time, there was a very obscure line of research called mobile agents. at a time when mobile phones are not really very widely adopted. So people were thinking about how about we build some agents that are traveling to different devices to perform necessary trainings leveraging the local data there, and then move on to the next device and next device and so on. So the mobility about the agent that is performing the training locally at the data silo where the data is being stored, that was an idea that was developed 17 years ago. Didn't really catch on at that time because of the virus-like behavior of such a software. So later on, when federated learning started to gain prominence in recent years, people revisited this idea to say, okay, how about we move training to the local devices, but instead of asking an agent to go around the devices to train in a serial manner to leverage data one by one, we just move the model training load to whichever data silo or devices that hold the actual data locally, without asking them to have an agent which moves across multiple devices. And then instead of moving data around into one location for training, people just perform necessary local training. There could be a lot of things going on. Later on, I'll talk about in my talk. You could need to perform local data selection in order to choose the most useful subset of the local data to support training of a particular task. And then once that's done, the partially trained model parameters are then passed back to the server for aggregation. That's the horizontal way of training, assuming that everybody is sharing the same model architecture. And then you could perform aggregation of the models, like performing a model parameter averaging to obtain a global model, which is then passed on back to the clients for further training or for any necessary personalization which need to be performed locally over there, not at the central server side. Of course, along the way, the parameters that are being passed, they need to be protected properly. Like Professor Yang Qiang's talk just pointed out, if you transmit plain text across such a potentially unsecure communication channel, people could intercept that. They could try to connect multiple interceptions and try to make out what kind of local private information can be derived from that. This is especially easy for situations where the data structure of the local parameters, of the local data sets are well known, like images. You know the data structure used to represent images, and you can, through multiple interceptions, try to figure out potentially what kind of images there are in the local store. So a lot of research is focused on protecting such a transmission, like homomorphic encryption, DP-based infusion of randomness, which potentially could hurt model performance. And people also think about what about we don't transmit anything at all? Instead, we use data distillation to transmit the distilled knowledge through a common data set, which is public. We don't have to worry about any leakage there. So there are a lot of works going on at that part. So federated learning privacy protection is very well researched in terms of the horizontal situation, horizontal arrangement. For the vertical arrangement, they need to focus on a different situation where different data silos, they each hold a different model. It's like Alibaba trying to collaborate with DBS. So the data features are completely different. Could be a little bit of overlap there. So they cannot deploy the same model across these two silos. Then they have to worry about, okay, how to transmit intermediate results. So instead of model parameters, intermediate communication, intermediate results are being transmitted. Like, for example, if I see this sample, this person is trying to apply for a bank loan. I have a partial picture of this person in Alibaba, partial picture about this person in DBS. Maybe we each have a vote to say, okay, whether we believe this person could be a fraud or not. Then we could need a third party, a third entity there, so that the intermediate result of for example, the voting mechanism would eventually decide whether we give this person a loan or not. So there's different arrangements for that. Okay, thanks. Any other questions? Yeah. Okay.
Oh, thanks for me. So, federated learning has been quite inactive for 5 or 6 years, right? So, there has been a lot of research and the results established for example, the privacy-preserving DPI and DCE, the model aggregation, communication, or even some fairness incentive problems. So, my first question is like, so many research has been felt there. Now, federated learning area has been very competitive. So, what will be some future open gaps, open challenge and research gaps you would like to recommend? Maybe have more opportunities for for maybe next few years. This is my first question. The next question is that do you think there will be one day that the federated learning come to the end of this life cycle? Would it be possible, or maybe another answer that would that be like a lifelong training for the FL? Yeah, thank you.
So the first question I will answer in the talk, okay, which is coming up. So the entire talk is talking about future perspectives, which we discovered from some of the ongoing works that we have been performing in collaboration with the industry. Okay? So you'll see a lot of things there, like combining federated learning with graphs, combining federated learning with auction, to build a trading marketplace for data or models. So later on you'll see more details there. And in terms of whether eventually this field will mature into a state where no more research is needed. I think when you see the Gartner hype cycle, almost all the topics we look at will go through such a hype. Like 10 years ago, there was a very active field called cognitive radio in communication research. So before the device was even built, we had 5,000 papers published, envisioning what's going to happen if we infuse reputation, trust, whatever things into this fancy technology. So there's bound to be this period. So federated learning today is in this period when things are not fully designed yet. In terms of how exactly is the best way of doing things, we don't know yet. So there are a lot of things being proposed, a lot of different directions being explored. So that's natural for any field in its beginning, in its first few years of exploration. So people are trying to explore different areas. So people from different backgrounds, they're coming in to say, okay, I see something which in this field, which is similar to what I've been doing in another field. Can I try this here? So this is a very healthy period of time when interdisciplinary work is being carried out. Okay, so along the way, consolidations would be made. You can see the effort of standardization, either through IEEE or through some other organizations. People are trying to standardize. Okay, if we want to deploy this technology into real-world usage, we cannot just say, okay, there are so many directions being explored. Let's look at all of them and try to put things together ourselves. Many companies, they don't have such a capability or time to do this. So the standardizations would be useful to help us highlight what are the most important key components that if we want to build a federated learning for a particular purpose, we need to have them. And it's also a way to protect the companies from any potential responsibilities they have to take if things don't go perfectly. So they have the standardizations to fall back, to say, okay, this is how we followed this standardization to perform, to design our solution, and we know the boundary of the performance there. Maybe through such an effort over time, the way of deploying federated learning would be more or less stabilized over time, like what we are doing today with the recommender systems. So nowadays, we still can publish papers in recommender systems, but the major structure of performing recommendations, the big companies like Alibaba or Shopee, they are pretty much set in a particular pattern. Okay. So sooner or later, we'll reach that stage. Okay. I don't know how long it will take, but the pattern of all the research directions to explore now. Yes. Any other questions?
Yeah. Thank you for this very informative answer. Yeah, actually, okay. Thank you. Yeah, actually, my question regarding Professor mentioned about some key components in federated learning. which is, I believe, require different backgrounds, and I think for someone to have like some strong knowledge in all these areas, it can be quite challenging. So my question, like people who are like, for example, people in distributed ML, people in model design, or game theory, or people in wireless communication or communication in general, do they have the same interest in federated learning? I mean, the progress. Maybe like people from one area are more interested, but they will not achieve like complete success without being other like people from other areas interested in this area. So is the progress is similar, like all the people from these areas are interested in federated learning? If not, how can like we encourage them, or we need someone to have like background from all these areas? This is my question. Thank you.
Okay, thanks. It's very hard for anyone to have the full picture of this entire field because of the nature of this interdisciplinarity. Okay? So as you said, people from security and privacy background, they focused on attacking and defending the models. People from machine learning backgrounds, they're looking at how we can reinvent existing machine learning models in a federated pattern, in a federated manner. Okay? We see people working on federated continual learning, federated meta learning, metric learning. So they're looking at, okay, if we can do this with full access of data in a centralized way, if we change the setting into a federated setting, what kind of whether there are any fundamental changes we need to make to the original model. Okay? Machine learning guys are working in this domain. Economics and multi-agent systems, the people, they are saying, okay, why don't we think about this field as a marketplace? So people are trading resources. Resources could be data, could be computational power that you locally hold, it could be even the people they know in a social network whom the people initiating federated learning training tasks that they're trying to look for. Okay. All these are possible resources that could be traded. So they're looking at multi-agent reinforcement learning, game theory to look into how to optimize such an ecosystem. Communication guys, they're looking at, okay, there's communication channels involved in this architecture, so how can we protect such a communication channel? How can we ensure if there's any asynchronarity in terms of the transmission of the model across multiple devices? How do we handle that? What if somebody drops offline halfway through training? Can we still go on with the rest of them? What if someone had a long delay and transmit an updated package to us where we already went through several cycles of aggregation? So do we still leverage this stale update, or do we throw it out completely? So how do we make such a decision? Or even, how do we protect a communication channel from being eavesdropped by some third party? So I even have researchers working on quantum federated learning. So we're trying to leverage the quantum mechanics properties to see how can we detect situations where the communication channel is being monitored by someone, being observed by someone. How would the qubits change? Okay, so they're exploring all these directions. So it's going to be very difficult for any individual person to put everything together into a working solution. But later on in my talk, I will introduce our lab, which is called Trustful in NTU. We're trying to put several of such aspects together into a sort of a solution which eventually works towards making federated learning trustworthy. You hear about this term a lot. There are groups in Vancouver, in UIUC, in Hong Kong, in JD, in Singapore. They're all talking about trustworthy federated learning. Okay, so basically, the main idea is to combine responsible AI aspects such as explainability, robustness, security, privacy, fairness, and so on and so forth into this full spectrum, so that eventually we hope that the models built by federated learning would comply with all these requirements. All to minimize the resistance from societies in terms of accepting these new technologies. New technology doesn't mean federated learning. The new technology we refer to is AI itself. Okay? So if we want to persuade the society to accept AI, Now the argument is saying, okay, AI needs to be trustworthy. Whether it's built in a traditional centralized manner or built through federated learning, we want the eventual product to be trustworthy. So can you show us how to do this? That's why the topic of this workshop, trustworthy, trustable, verifiable, and auditable federated learning, all to present to the society, to the authorities to say, okay, if we have this kind of capability, we can prove it's trustful, we give you the tools for you to audit and verify our process as well as the end product, the models. Can you allow such a technology to be deployed in the society? Okay, very interesting question. Thanks. Any more questions?
It's okay. I think my question is, how do you see currently federated learning and there's another thing called obvious computation? How do you see these two come into play? Because most of the federated learning I only see what they are doing mainly is on MPC or on top of homomorphic encryption. But on top of obvious computation, there's not a lot of work on that particular area.
I'm not very familiar with this, but I heard about this term before, oblivious computation. I don't exactly know how it works, but correct me if I'm wrong, but it is a type of privacy preservation technique, right? Okay. When we try to incorporate privacy preservation techniques into federated learning, there's always a trade-off which needs to be made in terms of supporting the training process, which is already in place in our industry partners, as well as ensuring that the end model is valuable, the performance of the model is acceptable. Okay. So the process in terms of training the model, we need to ensure that privacy is being preserved. We cannot really achieve 100% privacy preservation. The privacy preservation will come in different levels as well. And eventually when the model is to be deployed by the industry would want the model to work well. Okay. So I'm not sure exactly how oblivious computation works in terms of affecting the training process, how much overhead it adds on to the training process itself, as well as how much it impacts the eventual model performance. In our experience working with industry partners like Alibaba, which are training huge models across its multiple subsidiaries in Europe, in China, in Russia, solutions such as homomorphic encryption, they're not going to consider that. It's not going to work on such huge model parameters. The communication overhead is huge, computation overhead is huge, and we cannot really ensure that on such a big scale, HE still works when you try to aggregate such models together. So we have to find other solutions. And in that case, a lot of work is focused on dropout and quantization techniques, which, if properly designed, would achieve the goal of protecting private information and at the same time reducing the communication cost. But of course, still taking into account of the model performance aspect. Some of the models, they focus on these first two aspects to over-optimize towards that, ensure that each round you transmit a really, really small percentage, like 6% of the total model parameters across. But then you have to transmit that for a huge number of rounds, but eventually you calculate the total communication overhead is still higher than if you did nothing. But by doing so, by only transmitting a very small subset of the model parameters, you make it very hard for any people who are trying to intercept your transmission to figure out useful information from the little bit of information that you are transmitting. So people are trying to say, okay, what if we do away with the DP, with the HE, with the privacy preservation techniques, but focus on compression, focus on quantization or dropout? Can we achieve both goals together of reducing communication and preserving the privacy. So a lot of work are going on in that direction as well. Thanks. We into the time of tea break. Okay.
Sorry, so I think you have shared some system platform and you're working with the industry partners to sort of deploy this system. So my question would be, in your opinion, how really trustworthy the system are, and how do you think that we are really ready for deployment, or do you think that there's a lot that needs to be done, and how long do you think that we will reach the phase that we can really roll out such system with confidence? Okay.
Because trustworthiness is actually a very multi-dimensional concept. When our industry partners talk about they want to build a trustable or trustworthy solution based on federated learning, we always want to ask them, so what is the most important aspect of trustworthiness that you want to focus on? Is it that the model should be as explainable as possible? What do we want? What do you want to explain? Do you want to explain how the model makes decisions? There's a set of techniques we can use, like neurosymbolic AI. We want to explain the impact of data points on the model performance so that you can make better selections locally of the data samples for training. That's another set of techniques we can use, like sharp and inference functions. Okay. What about fairness? Okay. Is fairness your focus? So what's the notion of fairness you want to focus on? There are 20 notions, well-known notions of fairness available, so which one do you want to focus on? Is robustness your focus? So which kind of attacks that you anticipate you would face more often when you deploy your model? So we need to optimize our solutions on, in terms of that aspect. So we always need to focus on the objective that you want to achieve and prioritize the trustworthy dimensions that we can incorporate into the FL training process as well as the eventual model that we produce. Okay. So there's no standardization on how to make a model trustworthy, or how to even prioritize different trustworthiness. So we did some research in terms of producing a brainstorming methodology to support a team of AI solution designers to see, okay, given the target, given the requirements that you have, given the target system you're trying to build, given the resources you have, how do you prioritize which dimension of trustworthiness or responsible AI that you want to focus your resources on? It's always going to be a trade-off. Unless you have an unlimited budget, you want to make a model that complies with all these dimensions. Otherwise, we always have to prioritize which one we want to focus on, which one we want to focus on less. Thanks.